Okay, good evening, everyone. I'm going to today talk about three topics of research that we're doing here at NASA Ames in astrobiology. The three topics: curiosity on Mars, plant growth mission to the moon, and a sample return mission to Enceladus. So three stories, three short stories. Next slide shows Curiosity, the big rover on Mars. It landed a little more than a year ago. So now is a good time to look and see what have we found. And I'm particularly interested in the search for organics on Mars, and so that's what I'm going to focus on. But first I want to mention, I think, some of the interesting highlights of the year, starting with the next slide, which shows the landing site. This is the landing site. I like to show it because we named it after Ray Bradbury, the science fiction writer who wrote the book The Martian Chronicles, which I think has been translated into just about every language, including Bulgarian. It's still the most popular science fiction book about Mars, 50 years after it was written. Ray Bradbury died just after the mission landing, so we named this rocket landing spot after him. You can see the dark area where the rocket exhaust blew away the light dust. And so it's darker because the light dust was moved away. It's not really burned. It's just been darkened by blowing away the light material. But it's a rocket landing pad, and I think Bradbury would have liked that because he liked rockets. And he named a book, R is for Rocket, and the first story in Martian Chronicles is called Rocket Summer. So that's the Bradbury landing spot, and this picture is one of my favorites because it shows the rover just starting off after 4 days of driving. And it's kind of an interesting off into exploration mode. The next slide shows what we did basically the first year. We covered 500 meters. Doesn't sound like a lot. A reporter once asked me, how does the pace of exploration on the rover compare to the pace of exploration with humans when we go out into the field, say in Antarctica? No comparison. The rover took a year to go 500 meters and drill half a dozen small holes. In the field, that would take a couple of students a couple of hours. They could do it after lunch but before dinner. But the rover is all we have. So this is the rover's traverse for the last year. We basically studied in detail two sites. One called Rock Nest, which was a sand dune, not very interesting from an astrobiology point of view. And the other site called Yellowknife Bay, which is very interesting. And that's the site I want to focus on. The next slide shows Yellowknife Bay. And this slide, I like this slide because it also captures one of the reasons why Mars is so interesting. This place, this picture, looks like many places on Earth. It looks familiar. You see in the distance the hills, kind of haze, foreground, rocks, desert surface. There are many places in Southern California that look just like this. So Mars always strikes us as familiar. But this site is particularly interesting for astrobiology. I'd say it's the most interesting site we've ever been at because of its history. It's a summary of the history of Yellowknife Bay sediments, the Yellowknife Bay sediments. First, when the crater formed, it filled with water. These are sediments that were deposited in that water. Very interesting. But even better, after they were deposited, they were buried. And even better, the rocks that buried them were removed only recently. The data from the rovers show that this removal occurred only 70 million years ago. We just really couldn't ask for anything better than that. Ancient water-laying sediments deposited on Mars in its early Earth-like period, preserved subsurface, not too deep, and then excavated recently by Martian history standards, only 70 million years ago. Next slide shows these sediments. These are the water-laying sediments, the mudstones that were deposited in the water. They're red, just like the rest of Mars, but we were hoping that this red would just be on the surface. And indeed, the next slide shows the first drill hole. And when I saw this slide, this image come down, this was the first drill hole ever done on Mars. It was certainly the first drill hole ever done in sedimentary rock. There it was, gray Mars. So on the surface, we see red Mars, but then just below, it's gray. That was, for me, a wonderful result. I couldn't have expected better. We had successfully gone down into the reducing primal sedimentary material. I was worried we'd have to drill a meter, but just a few centimeters, we reached it. Very exciting. When we took this image, I was sure that this gray stuff would contain organics. In fact, I said if we were there, it would probably smell like rotten egg, hydrogen sulfide smell, the typical smell of sedimentary material. So the next slide shows this gray stuff in our instrument being collected. So we scoop it up, we drill it, we scoop it up, and we analyze. What I'm looking for, or what I'm interested in this gray stuff, is the question of, does it have organics? But the story of organics on Mars doesn't begin here. It really begins many years ago with Viking. Next slide shows the Viking mission to Mars. They went to Mars to search for life and to search for organics. And the results from Viking seem to indicate that there was neither life nor organics, which was very puzzling. We didn't understand why Mars would have no organics, because organics, as I'll show later, are falling in to Earth and into Mars from meteorites. So there should be some low level of organics. That was the prime puzzle of Viking. Why no organics? The answer to that puzzle started to emerge only a few years ago with the Phoenix mission to Mars. Phoenix landed on Mars in the polar regions. This is Phoenix being assembled at JPL. Its mission was to dig to ice. The next slide shows that Phoenix indeed found ice, not a surprise. But it found something that was very much a surprise, and that is that the salt in the soil on Mars was all in the form of perchlorate. This is quite a surprise. The next time step will show us what perchlorate is. That insert shows a chlorine molecule bound to 4 oxygen atoms. That's perchlorate. It's a very reactive molecule. Summarizes some of the interesting properties of perchlorate. It's used in rocket fuel because it decomposes at high temperature. And that decomposition at high temperature is probably the explanation, well now almost certainly the explanation, for the lack of detection by Viking. Viking didn't detect organics because the organics reacted with the perchlorate as Viking heated up the sample to detect them. Perchlorates are also interesting because they make for a very good antifreeze. They are edible by microorganisms, and they are toxic to humans. They interfere with the thyroid. So it's really quite peculiar that on Mars, the salt on the surface is in this form of perchlorate. On Earth, of course, there's salt in most soils, but it's in the form of chloride, like sodium chloride, normal table salt, which doesn't have any interesting properties at all compared to perchlorate. The next slide takes us back to Curiosity. The instrument we're going to use, or that's on the rover, that we will use to analyze this gray stuff, is fundamentally the same as Viking. It heats the sample up to analyze the organics. Well, just like Viking, heating up the sample can destroy the organics because of the perchlorate. So this is a problem that we didn't realize until after this instrument was built. So there are still several modes of operation of this instrument that will allow us to detect organics, I think, and I've listed them here. Most importantly, we can scan in temperature to very high temperature. Secondly, we have carried along some reagents which allow for liquid extraction, not just thermal extraction. This instrument has a chance of detecting organics. Next slide shows the results from the Yellowknife Bay samples. And you can see two very interesting features. Well, three. One is release of water. There's bound water in the soil, not a surprise. Then there's a high temperature release of water. We think that's due to clays, so the soil is clay rich. We see a hydrogen sulfide coming out at high temperature. So yeah, it would smell like rotten eggs. And we also see the oxygen coming out around 300 degrees. That is the signature of perchlorate. So there are perchlorates in this gray stuff. That was a surprise. The zone over which we could still in principle detect organics. At very low temperature, we could see the organics before the perchlorate comes active, and at very high temperature after it does. The next slide shows that we did detect organics. The problem is that the organics we detected seem to be completely dominated by contamination in the instrument. As it happens, one of the chambers full of reagent, MTBSTFA reagent, leaked. And that reagent is reacting with the perchlorate and producing all of these organics. So the challenge for the team is to compensate for this contamination and determine if there's any organics that are indeed Martian. It's very hard to do that. Next slide shows why we expect organics. Just summarize what I said before. Meteorites are falling into Mars. There should be organic. This has nothing to do with biology. If there's biology, it would add additional organics. So right now, I'd be happy just to find organics associated with meteorites, aromatic, kerogen-like organics. So that's what we're looking for. The next slide is sort of my summary of what we've done with Yellowknife Bay. Proving very hard to detect organics because of the perchlorate, because of the contamination. In my opinion, we may not succeed because of those problems. There's some hint that the organics are there at very low level. There's some hint that they're kerogen-like organics, like you'd expect from a meteorite. So the next chance to do such a detection will come on the European mission, ExoMars. But they need to learn from our problems with the perchlorate and our problems with contamination. Now, the rover is on its way up to Mount Sharp. So we have left Yellowknife Bay, we've left the sediment, and we're going up the mountain. I'm not sure we will find anything on the mountain that's more interesting for astrobiology than the bay, but I hope we'll see. So that's the status of Curiosity. Maybe next year we'll have new results if we hit something interesting on the side of the mountain. Okay, story 2. This one is about the moon, and it's about life on the moon. And the point of this slide is to point out that the moon, the surface of the moon, is a unique environment in terms of gravity and radiation. The next slide is to remind you that indeed we have sent humans to the moon. We know that people can be there for a few days, but we don't really know about living on the moon for a long time. So what we are proposing is to grow plants on the moon. And the motivation for that, listed here, is first, plants are indeed multicellular organisms, so we would learn about how life survives in such an environment. And 2, growing plants is necessary for life support. The next slide shows, this is just a summary of work that's been done so far on growth of plants at lunar gravity. There has not been very much. Next slide shows why this is an opportunity. It's not an opportunity because of a NASA mission. It's an opportunity because of private missions that are being produced in response to the Google X Prize announcement. So Google, which is our neighbor, they're right next door to us here in Silicon Valley. Google has put up $40 million as a prize, or a set of prizes, for missions to the moon. So there are a lot of companies, a lot of groups trying to win this prize. And we have gone to all of them and said, when you go to the moon, would you take our little plant growth module? So the next slide shows our concept. We want to build, or we have already built, a small plant growth module about the size of a can of carbonated drink. And in that would grow plants, add water, and that would be the first step toward greenhouses on the moon and Mars. Next slide shows the science that we will focus on. 3 aspects of plant growth in a very short mission. 1, germination. Germination is essentially birth for the plants. If there's no germination, nothing else matters. So germination must be confirmed. But once the plants have grown even a little bit, we should see 2 characteristic behaviors of these plants: phototropism and circumnutation. Phototropism is the tendency to grow toward light, and circumnutation is a small little dance that seedlings do as they're growing. So we will be able to document both of those. The next slide shows our chamber. Very simple. It's just a container sealed with earth air on launch. There is no air revitalization. There's no air change. There's a little tank of water. Once we land on the moon, the tank of water sprays water onto the plants. They start to grow, and we take pictures. Very simple. It's so simple that we expect thousands of elementary and middle school kids to build duplicates of it and provide control experiments here on Earth. The next slide shows what the base of this experiment will look like. The diameter is about 10 centimeters. It's very small. But on that 10 centimeter disc, we can grow 200 or 300 plants of a species called Arabidopsis. Actually, that's the genus name, Arabidopsis. It's a standard plant that's used in research. So we could grow hundreds of them on this little disc on the moon. Look for germination, phototropism, and circumnutation. Next slide shows the sequence of the experiment. It lands on the moon. Water is introduced onto the chamber. The plants germinate when they see water. They don't germinate without water. They start growing. The experiment lasts for about 7 days, 8 days. Plants have grown several millimeters high. They start to do their phototropism and circumnutation. We've taken pictures. That's the end of the experiment. It's just the very first step of showing plant growth on the moon, and we do it as a NASA payload on a private mission. And it's enabled by the private mission. If NASA were to do a plant growth mission to the moon, and I've argued for that before, it would cost $300 million, $300 million. If we are just doing this experiment, it will cost $1 or $2 million. So we do a small experiment for much less cost. So it's a new way of doing science, I think, that is enabled by private mission. Okay, and we have already built this module, and if you're familiar with the Google X Prize rules, or if you read carefully the chart that I showed, these missions launch by December 2015. So this experiment will go on those launches in about a year, 2 years from now. So next slide is the third story. Story 3 in astrobiology here. This is a mission that's in the future. My favorite world right now is Enceladus. Even from an astrobiology point of view, even better than Mars. And the reason is that there's a jet of water coming out of Enceladus. The next slide shows where we think this water is coming from. It's coming from a subsurface ocean, coming out through the ice, venting. Next slide shows some results from Cassini, which show not only is there water coming out, that water has in it nitrogen compounds, organic compounds. It's not water, it's soup. It looks just like what you might imagine a primordial prebiotic soup might look like. And so it's very interesting. Ask the question, is there life? And so if we look at the next slide, I want to point out that Enceladus, small moon of Saturn, is the most habitable world we know of in the solar system. It is, I give it a gold star. Enceladus gets a gold star because it has all the major requirements for habitability. So Enceladus has all the things we're looking for on Mars, all the things we hope there to be on Europa. Here they are on Enceladus. We know that they're there. And not only do we know that they're there, but they're coming out into space in a plume, which makes sampling very easy. We don't need a drill. We don't need a melter. We just need to fly through and collect it and bring it back. So I think this is a very exciting opportunity. The next slide shows what we're trying to do. Hayabusa, the Japanese mission, was a sample return to an asteroid. Well, we want to do essentially the same thing to Enceladus, a sample return. So we are trying to form a partnership. And the reason we want a partnership, not just because there's technical capabilities in both countries, but also because we're trying to keep the costs down. From the NASA side, we want to fit this mission into a discovery class opportunity, which means that we need to partner with the Japanese so that they can share some of the costs. So my concept, which is not yet approved, so to speak, is that the US would build the orbiter and the Japanese would build the probe. And that way it would be similar to the way the US and Europe did the Cassini mission. So this would be a very exciting possibility to bring a sample of this soup and the plume of Enceladus back to Earth.